Hey, welcome back to your favorite calculus class. We're going to look at limit of a function and some limit laws. Let's talk about first the graph of the function x cubed minus 1 over x minus 1. What we're going to do is we're going to look at the behavior around x equals 1. So if you notice, like, we can't plug in 1 obviously because we'll have a 0 on the bottom, right? This function, in fact, if you remember back to pre-calculus, if you were to factor the top a cubed minus b cubed, it factors in a squared plus ab plus b squared. So you got this, which means it behaves like, so f of x graphically behaves like this quadratic, except has a hole at, right, if these cancel, right, if you get this rational function with those binomials there canceling, then you have a hole there at x minus 1 equals 0. In other words, at x equals 1, because 1 makes that undefined, right? So we have a hole. So this thing looks kind of like, if you were to graph this with 1, you got this hole right there, okay? In fact, let me pull it up on Desmos.com and kind of look at that here. What we're going to do is we're going to analyze this. F of x equals x cubed minus 1 divided by x minus 1. Okay, you see that? You can see there the quadratic, right? It behaves like a quadratic, except it's got the hole at 1, 3. In fact, let me put in a table here, and you can see at 1, it's undefined here, and it's got these other points, you know, negative 2, 3, plug some points in for 0, 1. We could plug some more in. But what we're looking at is I want you to look at around 1, as I get close to 1 here, what's it approaching? So as I approach 1, if I was to plug in 1.27, I get 3.883. If I plugged in 1.24, I get 3.778. The closer I get to 1, I know at 1 I'm undefined. See, there's the 1 undefined. See that hole right there. But what am I approaching? What am I getting arbitrarily close to? And that's the question of a limit. Pull this back up again. That's our question of the unofficial look at a limit, okay? The informal look at a limit is how is the function behaving around x equals 1? Again, if we plugged in something close to it, whoops. You know, these y values are getting closer and closer to what? If I do it from the left-hand side, you know, again, I know there's a hole, right? But I'm getting close to what y value as I approach it from the right, as I pick x values closer and closer, and then as I approach it from the left, what's it getting arbitrarily close to? What y value? And you can see it there. You're like, well, 3. Obviously, it must be 3. That's the limit. That's the informal definition of a limit. We'll talk about the formal definition of a limit. So here's how you write it. The limit as x goes to 1 of this function is 3. In other words, the limit as x goes to 1 of x cubed minus 1 over x minus 1 gets arbitrarily close to 3. Now I know the functional limit, f of 1, is not 3. We know that. There's a hole there. But we're getting arbitrarily close to it. From both sides, I'm agreeing from both sides. What y value is that? 3. Getting real close to 3, and you can see it with the table. Okay, here's just another look at it. So informally, as I approach 1 from both sides, are they agreeing on the y value? If so, what is it? Even if it's not defined there, what's the y value that it's getting closer to? Okay, that's the informal definition. If a function becomes arbitrarily close to a singular number, in this case 3, gets really close to a y value of 3, as x is approaching from either side, then that limit is 3. Right? If we are getting arbitrarily closer and closer to 3, we say that's our limit. All right, here's another one. So in this one, we've got this function, we've got the square root. Notice you can't plug 0 in either. With direct substitution, you plug it in, you got 0 plus 1, 1, square root of 1 minus 1. You got 0 on the bottom, right? This is, again, indeterminate. In other words, this thing's undefined. And so we've got a hole on this thing. In fact, here's a picture of it right here. We've got a hole right there. So the question is, as I approach from both sides, I'm trying to look at this limit as I approach an x value of 0. So as I pick functional values closer and closer from both sides, do they agree on a y value? If so, what is the y value? I know the functional limit does not exist, right? It's undefined. The functional value does not exist. But does the limit exist? Does it get arbitrarily close to a y value? We say, sure it does. What's that y value right there? It's 2. Now let's look at the table. If I was to plug in 0.01, I get 2.0049. If I plug in even closer, 0.001, I get 2.0005, and so on. And you notice I'm getting closer and closer. Oh my gosh. And closer. What is wrong with this thing? Come on. The y values from both sides, as I'm picking x values getting close to 0 from both sides, right? I'm picking an x value of maybe 0.01. I plug it in, I get 2.01. I plug in 0.001, I get 2.001 or whatever. And then from the bottom, right, I'm getting really close. So yeah, you say getting arbitrarily close. So that limit is 2. We'll talk about how to solve these algebraically later here. But let's look at, sometimes it's easier to understand the informal definition of a limit by seeing one that does not have a limit existing. So this is, we're looking at the limit of this function as we approach 0 of the absolute value of x over x. And here's our graph, okay? Now notice, if I was to plug in points getting closer to 0 from the right, like I plug in a half, I'd get 1. If I plug in 0.25, I get 1. If I plug in 0.1, I get 1. Anyways, these from the right, it's 1. As I approach 0 from the left, so I plug in negative 0.5 and I get negative 1. As I plug in negative 0.25, I get negative 1. You notice all these from the left, as I approach 0 from the right, it's 1, but as I approach 0 from the left, my y values, my functional values are negative 1. They do not agree. They gotta be going to the same spot. They have to agree on the same spot. So this limit does not exist. They have to agree from the right and from the left. Here's some more pictures here. 3 different functions. A, f of x. As I look at this limit of x squared minus 1 over x minus 1, as x approaches 1. Okay, so we're going to pick x values from the right. We're going to approach it from the right. And we're going to approach 1 from the left. And we're going to say, do they agree on a y value? Yes, they do. They're agreeing on a y value. So it's 2. Now, if I was to ask you, what's the functional value when x is 1? What's f of 1? You say, well, there's a hole there. It's undefined. If I plug 1 in to this, I get a 0 on the bottom. This is undefined. The functional value is undefined, but the limit, it's getting arbitrarily close to 2. It's agreeing. It's getting arbitrarily close to 2. Let's look at another one here, g of x. So same thing on this g of x, the limit as x approaches 1 of the g of x function. I'm just going to write g of x. So I say, okay, I'm going to follow it from the right. I'm going to follow it from the left. Do they agree? Yes, they agree on that y value, so it's 2. Now, what's the functional value? what's g of 1? When I plug 1 in for x, when x is 1, what's the functional value? The value is 1. See it right there? It's actually defined when x is 1, the y value is 1. G of 1 is 1. This is defined, but the limit's 2. It's getting arbitrarily close to 2. Now h of x, let's do the same thing here. Let's go the limit as x goes to 1 of h of x. As I approach from the right, does it agree if I approach 1 from the left? Yes, they agree. What's the value? 2. The limit is 2. What's the functional value? What's h of 1? What's just its functional value? It's defined. No problem. When I plug 1 into the function, 1 plus 1, I get 2. No problem. H of 1 is 2. So here, the limit is the exact same thing as the functional value because it's filled in, right? It's continuous. It's continuous. This one here is not continuous. It has a jump right here, doesn't it? So it's defined, functional values down here, but the limit's still up here. This one's not continuous, but it still has a limit because it's arbitrary. It gets arbitrarily close. There, so it still has a limit. So all three limits are 2, but if you notice, all three functional values are different. There. Here's some more. What's your limit? Let's do it as it approaches 1 again. I say, well, as I approach 1 from the right, does it agree from the left? Yes. It looks like it's approaching that hole. So the limit of this function, I'll call it y of x. Looks like this limit is 3. What's y of 1? Undefined. It's a hole there. Over here, as I approach from the right, as I approach from the left, the limit as x approaches 1 of this function, I'll also call it y of x, is 3. And notice it's filled in, right? It's filled in. So y of 1, the functional value, is also 3. The functional value is the same as the limit on that bottom one there. Okay, so you're not going to have a limit, right, in the non-existence if when I follow a function, let me give you a different one. Here's one. Let's say this is 2. The limit of this function as x approaches 2 of this function, I'll call it f of x, does not exist because if you notice from the right, it's going to this y value, whatever that y value is. As I follow it from the left, it's going to a different y value. So limit does not exist. In addition, if you have a function, let's say you have one with a vertical asymptote at x equals, I don't know, 3, 4, whatever I make this thing. And here's what this function looks like. I'll call this g of x function, okay? The limit, 1, 2, 3, 4, this is a vertical asymptote of 4. Limit as x approaches 4 of this function does not exist either. What it's doing is it's shooting it up. As I approach it from the right, it's going up. As I approach it from the left, it's going down. We'll talk more about infinite limits later in the course. And finally, if you have an oscillation right here, so the limit is x approaches 0. Okay, so as I approach it, notice it just keeps bumping it up and down, up and down, up and down, up and down, up and down. Okay, it's just oscillating, so there's no limit. There's no limit on this either. This one, notice no limit, it's shooting up, shooting down. So limit x goes 0, no limit. Here, limit as x goes 0, they disagree. No limit as x approaches 0. Okay? Alright, let's do some more here graphically. Find the following limits or explain why they do not exist. A limit as x goes to 1 of g of x. Okay, as we approach 1 from both sides, so here's our x value of 1. I'm going to approach it from the left. Okay, it looks like it's going to a y value of 1. As I approach it from the right, they're disagreeing. As I approach an x value of 1, if I follow this function from the right, it goes to 0. As I approach it from the left, it's going to 1. No limit. Limit does not exist. Okay, now let's do it for limit as x approaches 2. Limit as x approaches 2. Okay, as I approach 2 from the right, here's our x value 2. Let me follow the function from the right. Okay, it looks like it's going to a y value of 1. As I approach it from the left, looks like I'm going to a y value of 1. They agree. What's the limit? 1. There's your limit. Now the limit as x approaches 3. Limit as x approaches 3. Let me approach 3 from the right. Let me approach 3 from the left. Do they agree? Are they going to the same y value? You bet. That y value is 0. That limit is 0. And finally, now, what's the functional value, by the way? What's g of 3? What's g of 3? G of 3 is defined right there. It's 1 equals 1. So the limit's 0, but the functional value is 1 because it's defined right there. Okay? Now let's do this last one here. I've got, erase this as well. Limit as x goes to 2.5. As we approach, so here's 2.5, right? So as I approach it from the right, as I approach it from the left, it looks like this is, the slope's down 1 over 1, so it must be 1/2. Right? All right, so how can we find these limits? How can we find these limits? Because right now we've been finding them, we've been looking at the graphs primarily. We've also looked at the tables and we say, is this thing arbitrarily approaching something? Well, what you can do is you can kind of manipulate it algebraically. So for example, let me start with these first two. So the first thing is you want to say, if it's continuous, like a polynomial, all right, polynomials are continuous. So smooth and continuous. So when if I'm looking at this function, this quadratic, I say, well, I just got to plug in 2 and see what the value is, because the functional value is going to be the exact same thing as the limit. So I can directly substitute. So that's the first thing I do. I say, can I just punch it in, and as long as it's continuous, then it'll be the limit. So I plug it in. So I get -4 plus 10 minus 2. Looks like I get 4. So our limit, as I approach from the right, I approach from the left, that's a y value of 4. Okay. Now this one down here. So here's the trick on this one. You're thinking, well, I can't plug 2 in, so I try to directly substitute first. But this is a rational function, and it'd be fine if it wasn't 2. If it was like 1, I'd plug it in and I'd be fine. Right? If it was 0, I'd plug it in, it'd be fine. And that'd be my limit. But 2, I can't plug in. I got 0 on the bottom. So can we manipulate this algebraically? We know these rational functions, sometimes they'll factor. In this case, sure enough, it does. And we're like, oh, this is kind of like that first one we did, where this function, it behaves like x minus 5, except since these cancel, except has a hole at x equals 2. Right? So it's got this hole right there, but it looks just like y equals x minus 5. You remember from pre-calc when you did that graphing stuff, right, with rational functions. So I say, does it have a limit? You bet. I just got to find where that hole is, because as I approach there from both sides, it's agreeing, it's getting arbitrarily close to that number. So what we're going to do is we're going to use the simplified version. So we're going to take the limit as x approaches 2 of x minus 5, and we're just going to plug the 2 in. So we get 2 minus 5, which is what? -3. There's our limit. Our limit as x approaches 2 of this function is -3. Okay? So number one, try direct substitution as long as it's continuous. Okay? If it's not, if you've got a hole in there, see if you can factor the thing out. If you've got a rational function of some sort, factor it and then do it, right? Now again, if this was like, if I was plugging in just 0, I would just plug 0 in everywhere, and this would have been fine, right? It's just for 2 that you have to do that in this case. Here's your solutions on that. Here's another one. Now in this case, you can't substitute it in. We'd mentioned this one earlier. We're like, hey, I got a 0 on the bottom. 0 plus 1, I got square root of 1. 1 minus 1, I got a 0 on the bottom. So this is indeterminate. 0 over 0 when I plug 0 in for x. It's indeterminate. I can't factor this out, right? But if you're looking at the graph, you're like, wait a minute, as I approach 0 from both sides, I should have a limit. Can I do this algebraically? Yes, you can do this algebraically. So here's the trick. What you want to do is you want to conjugate this thing. Multiply by the conjugate, I'm sorry. I didn't mean to say conjugate this thing. You multiply the bottom by the conjugate. Now you can't just multiply the bottom, you got to do it by the top, right? Otherwise you're completely changing it. So this is the same thing where it's like 3 over 3, right? We're just multiplying this thing by 1. So now we got x square root x plus 1 times, and now I'm going to, on the bottom here, I'm going to FOIL this. So I got square root x plus 1 times square root x plus 1 is just x plus 1. And then outside, square root x plus 1 is square root x plus 1. Inside, negative root x plus 1. Negative 1 times 1, negative 1. Notice those cancel right there. And notice the plus 1 and the minus 1 cancel. So you got x square root x plus 1 all over x. Notice your x's cancel, which is you needed that to occur. That's why we multiplied by the conjugate. We needed that to happen right there. So then we can say, oh, this is the function it looks like, but with no hole in it. In other words, we found the function that's the same behavior, but no hole. This is the function. So now I can plug the 0 in. So I got 2. Like, there's our limit. Okay, of course you could have seen that with a table of values as well. But that's what you want to think about, you guys. So when you're finding these limits, you want to look at them all different ways. In calculus, well, in mathematics in general, you always want to look at problems visually, numerically, and analytically. Right? Visually, algebraically, analytically. Right? Geometrically, algebraically, analytically. All three approaches is a good thing in mathematics, right? It'll help you to understand the concepts better and so on. So you're going to try direct substitution. If direct substitution doesn't work, right? In other words, you're an indeterminate form, see if it factors. If you've got something with a square root, you're probably going to have to multiply by the conjugate to get that thing to work. Right, top and bottom, multiply by the conjugate. And that's your algebraic approach to finding them. Now here's your limit laws. Okay, the limit is x approaches c of f of x plus g of x. If this limit is L and that limit is M, the overall limit just ends up being L plus M. And you can read through the rest of those rules for limit laws. Okay. Now polynomials, as I mentioned with that quadratic, polynomials are smooth and continuous, right? So being that they're continuous, when you run a limit on a polynomial, you can just always use direct substitution. Okay. With rational functions, you want to factor it out if q of c is 0, if the denominator when you plug it in is 0. If not, then you can just do direct substitution. You can just plug it in. Now the squeeze theorem. So the squeeze theorem or the sandwich theorem here says if I have the limit, if I know f of x is always between h of x and g of x, right? And I know those limits as x approaches c, so the limit of g of x is L, and the limit of h of x is L, right? Notice the limits are L here from both sides, they're approaching L. Then I know the limit as x approaches c of the function by the squeeze theorem must also be L. Pretty intuitive there, right? And here's just some examples of that. The limit of the red one as we approach 0 is 1, both sides. The yellow one, the limit's 1. So the blue one that's squeezed between them must be this limit of u of x must also be 1, right? Just some more looks at that sandwich theorem. Okay, and then finally, if your f of x value, the functional values of f are always below g, then the limit similarly will be limit of x approaches c of f of x will always be lower than or equal to x approaches c of g of x. Thank you so much for listening. We will see you guys next time.